Right. Welcome to Microsoft User Group Singapore. This session is being recorded and live streamed to YouTube and Facebook. If you do not consent from being recorded, please disconnect now. And to ensure good recording, please mute yourself if you're not speaking. With that, I please welcome our host, Nescu.
Hi, Rivut. Thank you. Can you see my screen?
Yeah, perfect.
The presentation which I'm sharing?
Yes.
Okay. Hi, everybody. Thanks for joining us. Today I'm going to share the contact details of the organizers here. If you are first time coming to this session, we are part of the Microsoft User Group Singapore, where we organize different meetups as part of Azure Office and data communities. And when it comes to the Azure part or Azure Singapore, it's myself, Saktis, Rivut, and Sentamil who take care of organizing different events. So if you have any request for a session, or if you would like to present yourself as part of these community activities, feel free to contact us. We have also put the links to our Facebook page and the meetup and YouTube URL as well. In terms of what we have been doing in the past, these are the last 4 sessions we had. And if you look at the kind of sessions we do, we also try to diversify on the different kinds of topics related to Azure. You can find the recordings of all these sessions using the short URL there, bit.ly, Azure Singapore sessions, and you can find the recordings of all these wonderful sessions. What's coming up next as part of our user group, we have the distributed messaging patterns session next week by Cecil Philip, and the following week we will have IoT data architecture by Dave Glover. Apart from Azure Singapore, there are also other meetups which our MVP colleagues they are organizing, and here we can find the links to these meetups. So the data community, they are hosting the data sessions, and you can find the details here. We also have the Office 365 and the AI community or AI ML, and you can find the details of their sessions. Apart from the meetups, we also have some boot camps which are coming up. And on 23rd and 24th, there is the AOS Southeast Asia event, which is happening. We have more than 40 different speakers speaking at this on these 2 days events. And as I understand from Rennie, who is one of the organizers, we already have more than 550 registrations for this event. So if you are interested, please feel free to register for this. We also have the .NET Dev Summit coming up on the 31st of October. And in the first week of November, we have the M365 Bootcamp. So if you are interested in joining our YouTube channel, put the QR code here. We have the recordings of all these sessions, not just the ones related to Azure Singapore, but also the other user groups which are running their sessions. And apart from the meetups, also events like Azure Bootcamp. So you find all these wonderful recordings of the previous sessions available on our YouTube channel. Please subscribe. Here are some of the most common or most popular sessions from our user group. Now, coming to today's session, we have machine learning at scale with Apache Spark by Adi Polak. She is a senior cloud developer advocate with Microsoft, and I've put the links here to her the social media handles. Now, before I hand it over to her, a few reminders or housekeeping. Please keep yourself on mute while the session is going on. If you have any question, use the raise hand feature of MS Teams. During the session is going on, you can unmute yourself when the Q&A is on. This session is being recorded, and if you find these sessions useful, please help spread the word using your preferred social media channels. So with that, I would like to hand it over to Adi.
Awesome. Thank you so much. I'm excited to be with you today. I'm going to share my screen. Just a second, here it is. Let me know that you can see it. All right, so do you see my screen?
Yes.
Awesome, great. So thank you so much for introducing me. For anyone who didn't, hear, my name is Adi Polak. I work for Microsoft. I work as a senior cloud developer advocate, and I specialize in distributed data and machine learning at scale. And today, this is exactly what we're going to talk about. We're going to talk about how we're going to do AI at scale. So I hope you're excited. So we need to start from the beginning. what does it mean to do AI at scale? AI at scale actually means we have a massive amount of data, we have a massive data sets, and we want to build an intelligent product. We are okay with the analytics part, we are okay with the BI part, but we want to take it like one step forward and say, hey, we want to really leverage machine learning and build something more intelligent with the products that we're building. And today we see more and more companies saying, hey, how can I adopt machine learning? Oh, but I have a big data, like it's really huge, a few terabyte or petabyte or anything like that. What can I do with it to actually make it available? And today we're going to talk about the different tools. We're going to talk about Apache Spark, and we're going to talk about what does it mean to leverage managed service such as managed Apache Spark service such as Databricks for production, how we can build machine learning with Apache Spark using something we call pipelines, what are cognitive services, how they can be integrated with Apache Spark. And also we're going to touch about the very delicate question of what's the difference between a data engineer, a data science, and now we even have machine learning engineer, machine learning architects, and all these titles are continue to evolve throughout the years. And we're also going to talk about an open source that Microsoft released, MML Spark, that's going to be at the end. All right, so what is Apache Spark? Apache Spark is known to be a compute engine that helps us do compute on massive amounts of scale. It developed in UC Berkeley back in 2009 by some PhD students who decided to turn it into a company that you might heard of named Databricks. And this is how Apache Spark started. And the nice thing about it is it's enabled us to do compute on multiple kinds and types of data sets. For example, I can do compute with Apache Spark on top of Elastic, on top of Kafka, on top of Redis, Cassandra, all of these and more. And the way that it does it using something called Apache Spark connectors. And we can also develop our own connector if you want, but the community already supported most of the connectors that we need. And also on Azure, we have connectors to Cosmos DB, Azure Data Explorer, and other different databases that we have. So most of the time you don't even need to think about it. You just need to know that, hey, I can use Apache Spark to run compute on massive amounts of databases. And there's probably going to be a connector that I'm going to use that already exists through the open source world. And a little bit of a motivation of what Spark gives us. So it's right, it does compute at scale, but how does it actually translate to what we need? So it helps us do something called data preparation. Let's say we have a massive amount of data that we're ingesting into the system, and we need to clean it, we need to organize it, we need to prepare it. And usually we do it using techniques called ETL. ETL stands for extract, transform, and load. So basically we're extracting the data from a specific source, we're doing some transformation on it, and then we're loading it somewhere, maybe in a dashboard, or syncing it into a new database that later on the machine learning folks can take it and use it. Another great feature is the real-time processing. So Apache Spark enables us to do near real-time processing using what we call micro windows, and it also enables us to monitor different streams that comes into the system. It's really great if we have some financial transaction and we want to process it and maybe detect some fraud on it if there is anything malicious. So it's a great tool for that. Another great feature that we can do and work with Apache Spark, this is the machine learning part. So Apache Spark comes with a library named MLlib, and MLlib stands for Machine Learning Library. So if you Google for Spark MLlib, you can find how you can build your own machine learning models using Spark MLlib. And it's also already implemented multiple algorithms out of the box that does it at scale. And what does it mean, does it at scale? We'll touch in the next slide. And the last one, it enables us to run different notebooks like Jupyter. So we can run our Jupyter, write Spark code, and immediately take back results. So this is part of the interactive query. And Spark enables us to do it using Spark SQL, for example, or other interactive mechanism that builds in. So these are just 4 things that helps with what we can do with Apache Spark. Of course, there are a lot more stuff like graphs computation, and now there are also deep learning computation and a lot of other things we can do. So this is just high level of some of the things. And how it looks like, well, this is a high level of the Apache Spark architecture. What we have on the left, this is the green part, this is the driver program. And the driver program runs on its own node. And on the right, you can see we have different worker nodes. And the worker nodes run on their own nodes, on their own machine, or if we translate to the cloud, on their own VM. And inside of them, they have something called executor. And the executor are executing tasks that the driver program asks them to execute. So when we are writing our code, the driver program take this code, compile it, understand what we want to do, and then send the request, send the task back into the worker. This whole system is called job. When I'm launching a job, I go through the Spark context, the driver program, it's split it into tasks, and send it back to the executors, and then I can get back my answer in the driver program. Or if I want from the executor, I can save it to a disk, to a storage, to anywhere that I work with. And to control all of that, because we're working in a distributed system and we have multiple VM, there is something called the cluster manager. And the cluster manager can be many things. It can be Yarn, it can be Mesos, it can be sometimes even Kubernetes. Now there are a few operators for that as well. So this is a high level architecture of how Spark builds it and how it distributed its jobs. Let's look at it in another way. Here we have the Spark driver like we saw in the beginning. And we have two different jobs. We have the green job and we have the yellow job. And we have multiple executors. Like we said, each job is being split into multiple executors. It can be that different jobs will run on the same executor. Different tasks from different jobs will run in the same executor, like you see here. But what actually is, the things that we most care about is the storage. So the tasks are being distributed. And if you see a green task, it means it's equal to the other green tasks in the other executors. But what is different is the data that they work on, which means after the job is being compiled and split into different tasks, it sends to multiple executor, and each executor work on its own data, which means each executor probably going to have different results because the logic that we're sending it is based on the data. And later on, we can accumulate everything and do an operation called reduce, where we're taking all the results and reducing it and trying to bring it back to one result that we can later look at. So this is another way to look at Apache Spark, how it works. And if we take another view, we can look at the framework libraries. So there is the user programs in kind of a purplish lavender color that we can write in Java, Scala, Python, R. There is .NET as well. We can work with it directly from the console, or we can interact with it through JDBC if you want to. And then what we interact with, we can interact with the Spark SQL API and the data frame API. And this is all being translated into something called the Catalyst Optimizer. And the Catalyst Optimizer is actually translate everything. It's doing its optimization and translate everything to something called RDDs. And RDDs are resilient distributed data set. This is the very basic of Apache Spark where it runs. So once we interact with the RDDs, it means we already passed all the performance tuning that we need. From here going forward, for us as developers, there's no more performance tuning that we can do. And this is a very important point to understand, because especially when a lot of people ask, hey, what should I use? Should I use Python, or should I use Java or Scala to do my Apache Spark work? How is it translated? So this is exactly what it is. Like after passing the Catalyst, there is not a lot more that I can do. Sometimes there might be collision between the translating from Spark, from Python to Scala, but this is a totally other, a different conversation. And this is another way to look at it. That shows us how we can, how PySpark, this is the Python for Spark works, how the .NET Connect, how the interloop layer that exists that helps us connect different programming languages like R, Python, and .NET, And within, we have the Apache Spark core. And how it all works together, it works through something called embedded service. So if I want to introduce, let's say I want to introduce another language like JavaScript, I've decided I want to develop a library that will support JavaScript for Spark. We can do it using the Sparks, using a specific protocol that we can develop. Of course, it's up to us to define how the communication is going to work, how well it's going to work, how are we making sure it's well performed, so we're not losing anything in translation. Sometimes it can be a little bit hard just because how the JVM works, but just so you know, it's possible and it's definitely something that we can do. All right, so there are more APIs. Like we talked in the beginning, there is the streaming, and for using the streaming, we can use the libraries from Spark under structured streaming. And it gives us the ability to run stream processing on a structured data. Structured data means I already have a schema and I already know how my data looks like and I know what to expect. There's the MLE library. I want to train models at scale. So this is where I go. There is the graph frame library. I want to run different graph computations on huge data. Let's say I have the huge data set like Facebook has with all the users in the world, and then I need to run some computation on REST, and Apache Spark definitely can help there. And there is the TensorFrame, which is the TensorFlow for Apache Spark. So if you're experienced with TensorFlow, there is option to use that for Spark as well. And like we said before, there is the SQL, the Catalyst, the Spark core, and the data source connectors. Like I mentioned in the beginning, we have Apache Spark knows how to do compute on a lot of different data sets types. And it does it using the data source connectors, like you can see on blobs, on Hive, on Cassandra. It knows how to communicate with Parquet, and a lot more. And again, it's all open. You can find it a lot of different data source connectors that are open source by the community, and people are publishing it and sharing that knowledge, so people won't need to recreate, let's say, the Cassandra data source connector. And you probably wonder why Apache Spark and why now, and why it acts as the leading computation engine for big data today, and why it's growing so fast. And the reason for that, it's because it's really efficient. I don't know if you're familiar with the traditional Hadoop MapReduce that was in the past, where we, for every iteration we did on the data, we have to write it back to disk and then read it from disk and then do another iteration. Apache Spark enables us to keep everything in memory, which is fantastic. Apache Spark has the Catalyst optimizer, which helps us optimize our SQL queries, our machine learning queries, our graphs, and everything that we do directly with the Spark API. So this is another layer that helps us, be more efficient and faster. And then the low-level optimization is the Tungsten. And Tungsten is more in the RDD section, is something that we don't interact with. And there is a new optimization, but this optimization is available on Databricks cluster. And this is the Futon. Basically what they did, they said, hey, Apache Spark is super fast in the JVM world. What if we'll take it and translate everything we have back into C and C++? So they pretty quickly realized, hey, we can translate it and give it as the Databricks cluster. But this doesn't exist as a part of the Apache Spark open source, although the Apache Spark open source is still faster than a lot of more different open source when we really need a massive scale. So let's take a look a little bit at how the Catalyst work. So let's say I'm putting in some SQL query using the Apache Spark query API or a data frame. They both go in the same direction. From there, it goes into something called resolve logical plan. It's try to understand what the logical plan that we're trying to create, but it doesn't yet have any information about the data. So it's just trying to process the query that we're doing. It pairs it up after that with data from the catalog. And data from the catalog is the data from the database that we give it. So let's say I'm working with Cassandra, and Cassandra has some statistics on the data, how it's stored, where it's stored, and so on. So it paired up with that. And together they do the analysis. They build the analysis, giving the information from the query that I want to run and how it's stored and saved on the data set. And then it's going into a phase of a logical optimization. What can we do to make this specific query faster? And then it goes into a physical planning. Like we know, we're talking about big data, we're talking about distributed systems, which means my data is not stored only on one machine, it's stored on multiple machines. So what is the physical planning that I need to do to make it all work? Then it's not the end yet. It goes into cost model, and the cost model, again, try to predict what is going to be the cost in terms of where is the data, what should be faster, how should you run it, and what should we do. And then it goes into the code generation, because everything we saw now was still under the driver umbrella, but now we're leaping into what we're going to actually send to our workers, what task, how it's going to look like, and that through the code generation. And then it being translated into the RDDs. Like I said, this is the back, this is like the basics when we talk about Apache Spark, because from here, we don't have any more optimization related to a catalyst. So you probably wonder, how does it all work? Well, when I work with SQL or when I create a specific API, like I'm saying, I'm giving a query of I want to do join or I want to get some attribute from someplace, it's being translated into something we call tree. And the tree can have different leaves and different attributes and different functionality. And we can pair it up with a set of rules that can help us do it faster. So we can actually go over the set of rules and understand which leaves in the tree might not be so relevant, or where can we prune it, or do we actually need to run all of that? So this helps me optimize the amount of tasks that I need to do, the amount of operations that I need to do. Here, for example, I went all the way from having, to 1 or 2 depth level, depends how you're counting, into a 1 level depth tree, which is really useful because now I need to do less operations over huge data, which means I'm going to save A, a lot of money, B, it's going to be much faster. So this is how the catalyst work. We have kind of the front end. This is what us as engineering work with. There's the catalyst part, and then there's the back end, which is the RDD, the physical plan, and how it's all being translated. And there's a lot of optimizations, different optimization that you can look at, like predicate pushdown, specifically very important one because it connects well to the database that we work with. And if the database supports something called predicate pushdown, then it actually means we can do this calculation in the database, and we don't have to read from disk and bring all of that back to Spark cluster. And there are more optimization, and you can just open Apache Spark code, look for the optimizer library, and you'll see a huge list, and it's always being updated, and there's always things that are being added to that as well. So I definitely recommend looking at it, learning a little bit about it because it's an interesting topic. All right, and we said we have connectors, right? So there are also connectors to things like SQL Server if we want to. So if you work with SQL Server on Azure, there is a connector, and you can build it in a way that it reads that the worker nodes reads data to compute it from SQL Server. And of course, there's also a connector for Cosmos DB. So let's say you work with Cosmos DB and you want to work with Spark because you have a massive amount of data. So you can configure the connector for Cosmos DB as well. And this is open source, so it's always nice to go and see how it's done. And also there's a lot of tutorials on the internet on how to use it. So take a look, it's really interesting. And we know already that Spark is something that we might work with if we have a huge data sets, and we know we need to run some workloads, but how can we use it on Azure, right? So we have multiple ways to run Apache Spark workload on Azure. We have the HD Insight, which gives us Apache Spark open source workload out of the box. And we have the Azure Databricks, which gives us the optimized Apache Spark workload. Like I said, they have their own unique IPs for different optimizations, like the Futon one. We have AKS, Kubernetes. If you want to run it, on our own, and you want to take the responsibility, we can deploy Spark on AKS and Azure Kubernetes Service. And the last one is Synapse. Azure Synapse is still in public preview. Hopefully, it will be GA soon. But what we already know and we can see from the public preview, they support Apache Spark open source pools. So that means that if I want to run Apache Spark open source pools and I already work with Synapse, or I'm looking into working with Synapse and I want to have a modern data warehouse, then this is another option for me. Today we're going to look at Azure Databricks, but again, if you're considering, I definitely recommend looking at the different options that exist. So what is Azure Databricks? I already mentioned a little bit about that, well, Databricks was founded by the people who started Apache Spark open source, and it's good for data science because we talked about machine learning, and it's good for data engineering, and it's good for BI because it helps us put together very fast report and dashboards, and it's good for everyone who wants to work with data. But what we have inside, we have the Databricks Workspace, we have the Databricks workflow, so if you want to schedule Apache Spark jobs, we have the Databricks runtime, who is optimized for specific workloads that we need. So if we need some machine learning or anything like that, there's also different combinations of, and if we need the enterprise security part and the IO, it enables us to connect through something called GFUtils if you want. And there are multiple applications that we can do with it, which we already discussed. But how do we build it for production? So it's important to know that Databricks has different limits that comes from the Databricks itself and comes from Azure itself. It's important to understand the workspace isolation, what it means to have a Databricks workspace. We also need to know and think about the VNet, virtual network, how we connect things. What is the security that we need? Do we need a key vault to connect to different databases? And how we enable logs analytics for monitoring. So these are the limits that I collected for you. This is for 2019. I'm still waiting for the updated ones. But if you're interested in looking more into it, I recommend looking at the limits and understand how it translates to the workloads that you need. Most of the companies are not reaching that, having 150 concurrent jobs running in parallel on only one workspace, or having more than 150 notebooks that are live at the same time. There are very high numbers. So most of the time it shouldn't be an issue, but again, you should know that this exists. And then when you talk about working with Azure, we can talk about the different isolation. How do we isolate the subscription from the resource group, from the user that actually uses? If I want to have isolated workspace for my machine learning folks, for my data engineers, or if I want to have an isolated environment from a software developer team, then I can do it. It's enabled. And there are multiple cluster modes that we need to consider. There is the standard cluster mode, and there is the high concurrency mode. And all of them supports different feature and good for different things. If I have, let's say, I want to do more interactive query, then I might look into the high concurrency mode because I want faster results. Or if I'm building ETL, some simple transformation from data from one place to another with some logic in between, but it's a schedule. Let's say it runs every hour, then maybe the standard mode will be good enough for me. And also a lot of our options that we can look at, and it kind of brings us to this place of usually we distinguish the things, and we say we work with the batch processing, and we work with an interactive processing workload. And interactive means I'm writing a query, I'm getting a response right now. Batch means I have a scheduled jobs. It's run every hour, every day. It produces something, but honestly, I don't need it at the moment. So this is how we look at the batch versus interactive workload. And it brings different requests. So if I do have the interactive workload, so it's more for data science and analysts. And how they work, they usually use a shared read data that they read information from. So they need a cluster that can support reading the data, so the data is not changing, but they need to be able to get fast results. So they would probably want something that is, we are enabling to auto scale. So let's say there's a lot of data that they need to process right now. So enable them to auto scale and finish the query faster. And we can also use a shared cluster. And they can use it together. But this is like a read data and a high concurrency mode. And then we have the data engineer who work with a more batch mode because they do more operations. They're not only reading the data, they're actually transforming it and then saving it back to a new data set that they work with. So they probably will need a fixed capacity of cluster most of the times because the workloads are predictable. We know what already exists. We know how much data we already ingested into the system, and they don't most of the time they don't need the auto scaling mechanism from that point of view. So this was a little bit about the batch and the interactive, and kind of a way to think about what we need, what should we use when we actually want to design or architect our system for production, by understanding who are the people that are going to use our system. And of course, we can never think about building a feature or a service or anything without collecting the logs and being able to monitor everything that we're doing. So it enables us, Azure Databricks enable us 3 levels of logs. There is the cluster event logs. It's what happened with the machine, what captures different lifecycle events of the machine. And then we have the Apache Spark driver and worker loads. This is more of the logic inside. It can be the driver lost connection with the worker, or the logic throughout some exception because we try to divide by 0 or something like that. And then the 3rd level is cluster init logs. That if the cluster didn't load up well, or there was some issue with the machine, and we specifically said we want a cluster with 50 machines, and if it's not with 50 machines, then the cluster fails. So this is kind of the troubleshooting that we have to work with. And this is just a high level of how a metric report for the whole cluster can look like. And we can define it from the analytics workspace. Again, this is an example of script. You can take it and use it later. And now we're actually reaching the most important part, the exciting part, the part of the machine learning. So when we're doing machine learning processes, we need to gather the data, to do the feature extraction, to clean and normalize, select the algorithm, evaluate the model, do some data visualization, and we need to do it all in repeat. So we're constantly repeating ourselves when we're building and developing machine learning. So what we can do to help us is use machine learning pipelines. And pipelines enable us to structure everything together in a big pipeline to say, hey, this is my pipeline, and this is how I want the different tasks to run. So it's really useful. And then we can use that with Spark Streaming, Spark ML, Spark SQL, MLflow. All of this helps us to make sure we can build the pipeline in a right manner. So let's say we're taking the data files and the data set that we have, we're ingesting it into our machine data, we're running. The next thing we want to run is some feature engineering, training, scoring, understanding what's going on. And then we can deploy it to be part of a batch job or anything like that, and use that machine learning model through our Spark APIs that we're already leveraging. And this is all nice, but usually in life, it's very hard to get a good accuracy. It's very hard to develop machine learning model that it's actually good for our for real life workloads. And we need to understand that, and that's perfectly fine. So we need a data science, right? We always on the look for data science, and data science is very hype, and for a good reason. It's hard to find good data scientists. And it's more than that. Our data scientists need tools. So when we are developing the system, when we're building it, we need to provide them with the right tools to be able to be successful. And they're not always need to develop everything from scratch. There's a lot of things that already exist. So they can leverage tools and stems on the shoulder of giants, literally. And one of the things and one of the tools they can leverage is the Azure Cognitive Service. And the Azure Cognitive Service gives us built-in machine learning model out of the box for different functionalities that we want to run, because it's already built in, someone already processed it. And it can help us understand where is our machine learning model is, what can we do, maybe enrich the data, do more feature extraction using our machine learning models, and kind of bring more information so we can build a better machine learning model that later on will translate into a better product and a better service that we're giving to our clients. And this is just a high-level list of the cognitive services. There are a lot of new cognitive services that are available today, from vision to speech to language to knowledge to search to movement to video processing and a lot more. But just to give you a high level of what exists today. And the nice thing about it is we can combine it. So we can give our data science the ability to use cognitive services to help them get started in their machine learning process. I will say it's, when we work with big data, we need to be mindful of how we work with cognitive services. The cognitive service, when we work with it, we pay per request or per set of requests that we're doing. And inside, there are some ways to send multiple requests or send some ID into it and say, we already saw this request. So there's a lot of different optimization we can do. This is for a totally different session, but here we're going to see how we can put it all together and actually take some information out of Twitter or out of our Azure Event Hubs and then process it and enrich it using cognitive services. So this is a Python code. This is, I used PySpark for it. And I basically, here you see, I created some headers and the language API URL to with the sentiment endpoint. So that will be my URL to call the sentiment. And you can see I have text analytics, which means, and V3 and sentiment, which means I'm asking for a specific type of request from the sentiment. And there's also an SDK. You don't have to use that. I just like to use it because it's easier for me. I already understand that. And then I need to construct a document request. So I need to give it the ID, and this is where we can, we can be smart about what kind of ID we're sending, just in case we already saw something similar, and also the text and the document itself. So this was the cognitive service side, and now we need to put it all together. So we can use, when we work with PySpark, we can use a functionality called named UDF, and now we can build just the functions that are going to extract that information from us. We're still not working with Spark. So we are extracting, the first one is extracting the sentiment. So we take the docs that came back from the cognitive service query, and I give it a specific sentiment type, and I tell them, hey, if this document is not available, please return back in this specific place in the document the confidence score for the sentiment type. And the get positive sentiment is a function that takes a text from somewhere called the extract sentiment to extract that from where we want. And now we're actually in the PySpark part, because this is where we're loading data that sits. Now it's on some file store that we have. So here you can see the format that I'm loading. I loaded a CSV just for the demo. I specified that it has a header, which means structure. So Spark knows to take the schema from the CSV file. And then I call infer schema and then load. And in the load, I'm giving it the path. And the path doesn't have to be a file path. It can be a directory path as well, or multiple directories. Spark knows how to find the data files within it, and extract the information that we want. So we're taking all of that and we're saving it into an input data frame. So the the value, the object that goes back is a data frame that represents everything we know and how we work with Apache Spark. And later on, I can enrich that data frame with positive sentiment. So I create a new variable, enrich data frame, positive sentiment. And the way I make this new data set available is by calling input.df and calling it with column. With column is going to add another column and actually create a new data frame that will consist the input.df with the new column that I'm giving it. And here specific, I'm calling to get positive sentiment with the input stream that I have, because it's a UDF user-defined function that I can call. So how it's going to look like, if we go back to the start, when I have my driver and I have my different workflows that I want to do. So everything we know already splits into different tasks. So this task is going to be split as well into the executors. This is why I'm saying here, just be careful with the amount of data that you're processing and be mindful of exactly what you're doing and how you're using this specific way to when you work with Spark. All right. Now that we understand a little bit about cognitive services, we understand about Spark, we understand about datasets, we understand about connectors, we understand about distributed compute. Now it's like, the hardest question is what is a data engineer versus a data science versus machine learning engineer or machine learning architect or software developer or anything of such. Well, this is kind of a high level of what it means. Usually data science will have very advanced math, statistic, machine learning, AI capabilities. And advanced analytics most of the time, and they will have basic programming. This is why a lot of them kind of tend to work with programming language such as Python, because it's more simple, there are more libraries, it's more easy to develop. Versus the data engineer has more advanced hands-on programming. Maybe they're coming from a DBA background. They really know how data works, how to structure it, what it means to build indexes for data. They understand the basics of distributed systems, what it means now to kind of send requests to multiple machines and being dependent on the network, and also making it resilient and highly available. They usually develop different data pipelines. So the batch processing part, the batch workload like we talked about. And most of them will have a basic understanding of how analytics work, especially with Apache Spark when we have the SQL capabilities. They will know how analytics is SQL, what join means, what other join, left join, and so on and so forth. But the main thing that they should all understand, whether it's a data science or a data engineer or a machine learning engineer or a machine learning architect or software developer that works in this world of AI at scale, they should all understand the different big data constraints. And big data constraints goes all the way to, it can be a specific functionality that sometimes we can just not do, or sometimes when we work with big data, it's very hard to not to rely on statistics. And many times we rely on statistics about the data that exists, because we can't really count every line or every entry in our data. There are a lot more constraints, but it's just important to understand that these exist. And what does it mean when we plan a machine learning model and we want to develop our machine learning model, how this big data constraints comes in. And also from the data engineer is how this big data constraint is going to impact the different data pipelines and analytics and advanced programming that they want to do. All right, and last but not least, MML Spark is an open source Microsoft machine learning for Apache Spark that Microsoft released a few years ago. It's really interesting to see how they combine cognitive services, how they combine multiple machine learning frameworks inside to kind of give a simplified way to work with all these workloads. And they also have a very nice demo how they kind of classify pictures and images and all of that. So if you're interested to learn more specific about this space, I recommend to go check out the MML Spark on GitHub to better understand what capabilities they give, and also try it yourself, and also if you're interested is kind of looking into how they did it and what they're doing, just because of it's open source and it's an open source. That's the fun about open source. All right, and if you want to learn more, there's the QR code that I use throughout this talk today. There is also, if you want to go to aks.ms /mlflow and Azure ML, MLflow enable us to kind of keep keep different experiments and track different experiments that we're doing and we're building with Apache Spark. It's really nice. It's really easy from a data science perspective. You can also check out AKMS Azure Databricks if you want to learn more specific about the environment. Recently, they have a free trial of 14 days. So if you want to try that out, you can. And also, if you want to try Databricks without Azure, Databricks has a community edition. So you can go to their website, download the Databricks community edition, and run it on your laptop and kind of start playing with Apache Spark. And if you're interested to see the code about the Twitter sentiment analysis in more structured way, aks.ms/Twitter sentiment analysis, there's step-by-step of how you connect, what you need to do with Twitter to be able to sign in to get a Twitter developer API credential. And then you can start playing with it and running different Apache Spark workload and enriching your data with sentiment analysis, cognitive services, Apache Spark. Start playing with Apache Spark MLE or tensor frames or anything that you want. Yeah, that's it from me. Thank you. And I guess now we have questions.
We had one question in the chat in between. So this one was before you moved on to the Apache Spark functionality, there was a request to talk a bit about caching in Apache Spark.
Yes. So caching is a very tricky part, and it basically it's recommended not to use it unless you really know what you're doing. So I'll start from the beginning. When we are loading the data frame, like I said, the difference between Apache Spark and the traditional Hadoop MapReduce is that it doesn't write to disk. It's right to keep everything in memory. And it's right to keep everything in memory for a given job or for giving workloads that we're doing with a specific data frame, which means if I'm going back to how the JVM works, I have the garbage collector, and when the garbage collector detects that the specific data frame is not needed, it removes it, and we can also, and it kind of give a signal to the Spark to remove it from memory as well. So what we can do, we can actually cache it. We can call caching functionality and ask Spark specifically not to remove this dataset from memory. What it means that all the executors are going to keep that dataset and that part of the data sets in their memory, and they're not going to flush it until we'll tell them to flush it. The issue with that is sometimes people are forget to flush it. People don't fully understand how the cache mechanism work, and also people try to run multiple workloads with multiple data frame with caching, which means if I have a machine with, let's say, a specific amount of RAM, and I cached something in the memory, it means that all the other workloads for other data frames that I'm running are not going to be able to use that RAM, which means they're going to use way less. Which means it's going to slow down my machines and slow down my processes. And when we work in production environment, and it's not only one. Usually, it's not only one software developer writing Apache Spark workloads, or a team of software developers that's writing and interacting with it. Then we need to be very careful when we're doing that, because sometimes multiple workloads will want to use multiple machines. So just if you have a very specific plan on how you're using the caching in your team and on your machines, then go for it. But again, it requires a specific plan, and most of the time, it doesn't really worth it because Spark is optimized enough to kind of do all the things for you.
Okay, thank you. I don't see any other question in the chat. Anybody else has any question which you would like to ask by unmuting yourself? Looks like no. I had a question around the Spark and the cognitive services. So Spark, when it came out initially, it was quite popular because of its in-memory processing as compared to the MapReduce, right? So it was powerful, or it used to give benefits because it tried to do as much processing in the memory itself instead of writing to the disk. Now, if we talk about doing processing using APIs or services which are outside the process of Spark, like making a REST call, which is to a cognitive service, does it incur any performance degradation because of this out of process communication?
Yes, absolutely. It depends on how long, because Spark will stay on and the executors will stay on until you get back a response. They can't finish their task until all the information is back. So if we're doing this REST API call from our executors, it means that our executors are going to be idle until they'll get back the information. So yes, absolutely right. This is why I try to kind of give another view of think how you're using it, how you're structuring it, and also there's a matter of cost for every request that we're doing there. So yes, absolutely right.
Just a follow-up question on that as well. There is this self-healing capabilities in Spark as well, right? If you're using RDDs, because of the data lineage and things related to the graph that it maintains, it can handle the failover scenarios. Like if a node goes down, it can schedule that workload onto some other available nodes. So in this case, if we are again going back to the REST API call, if something goes wrong with the executor, would it be able to recover from that?
From what I've seen, they are able to recover from it, but they will try multiple times. So they will try to communicate the same REST API multiple times on their own machine until they realize that specific machine is maybe not capable, and it also depends if the error was logic. So if the REST API returned an error, or something happened to the machine, like it got disconnected or anything. If it got disconnected, then Spark will easily, bring up another machine because it use a pattern called heartbeat that it constantly try to keep up with the machines. But if something went wrong with the URL that you're sending, then it will try to resend this REST API again and again and again, and it will not know that something is wrong unless you introduce it explicitly in the code, saying if I got a bad request, then continue, or give it a random score, or put an error that this specific entry got a bad request.
Okay, thank you. Any other question from anybody else in the attendees? We don't see any other question on the YouTube stream as well. Revit, anything on the Facebook side? Looks like no. So if there are no other questions, I think we can conclude this session here. Thanks, Adi. Thanks for your time, and thanks for this wonderful session.
Thank you, Nils. By the way, if you're interested in learning more about Apache Spark and different cost strategy for working with Azure Databricks, I'm doing a session at Spark Summit, the European one, so it will be time zone friendly for all of us. and highly recommend joining if you're working with Azure Databricks or looking into working with Azure Databricks and trying to kind of make sense of how to calculate cost, how to optimize it, and how to work with it.
That would be helpful. Do you have the link to the session?
Give me a second. Yes, so is it okay if I put it on the chat for everyone?
Yep.
Okay. Some reason it takes slightly more to load, but Neil shall send it over to you, and maybe you can share it with the others.
Yeah, sure.
So
I can send it with the notes of this session on the meetup. Also, I can put up that.
okay, cool. Here we go.
Yeah. Thank you. Thanks a lot. Thanks everybody for joining this session. I hope you will be able to join us in the future sessions as well. Thanks, Adi, once again. Have a nice day ahead.
Thanks. Enjoy your evening. Bye, everyone.
For joining from Singapore. Bye-bye.